When a jet engine fires up, the noise is overwhelming, a roar so loud it can permanently damage hearing from 100 meters away. But inside that noise is something surprisingly simple: moving air. A jet engine accelerates air backward. Because of Newton's third law, every action creates an equal and opposite reaction. The aircraft moves forward. That is the entire operating principle. But the way modern engines actually do it, and how efficiently they do it, is what makes commercial aviation possible at all. Air enters the front of the engine and is compressed by a series of spinning blades. These compressor stages increase air pressure by a factor of roughly 40 to 1. At the back of the compressor, fuel is injected and ignited. The burning mixture expands rapidly, roughly 1,000 degrees Celsius, and this hot, high-pressure gas drives the turbine blades at the rear. Those turbine blades are connected by a shaft to the compressor at the front, so the engine is self-sustaining. The turbine drives the compressor, which feeds the combustion chamber, which drives the turbine. The hot exhaust then exits through the nozzle at the rear, accelerated to high velocity. That rearward momentum creates the forward thrust. The faster the exhaust, the more thrust, but only up to a point. Here is where modern turbofan engines diverge from the early turbojets. In a turbojet, all thrust comes from the hot exhaust. In a turbofan, a large fan at the front accelerates a much larger volume of air around the outside of the engine core. This bypass air never goes through the compressor, the combustor, or the turbine. It just gets pushed rearward by the fan alone. On a modern high-bypass engine like those used on the A350, the bypass ratio is around 10 to 1. For every kilogram of air passing through the core, 10 kilograms bypass it entirely. More than 80% of the thrust comes from that bypassed air, not from the hot exhaust. Moving a large mass of air slowly is more efficient than accelerating a small mass very fast. Both can produce equal thrust, but the physics of kinetic energy means the latter requires far more fuel to do it. Early jet engines operated on the turbojet principle: a small amount of air compressed heavily, burned with fuel, and expelled at very high velocity. These engines were fast, ideal for early jet fighters, but extremely fuel-hungry. The Comet, the first commercial jet airliner, had a range of about 2,400 kilometers. That was the limit of what the fuel economics allowed. Modern high-bypass turbofans, the engines on almost every commercial aircraft flying today, work differently. They move enormous volumes of air at lower velocities. A Boeing 737 MAX burns roughly 40% less fuel per seat than the original 737 from the 1960s. A Boeing 787 can fly 14,000 kilometers without refueling. That range is entirely a product of engine efficiency. The core of a jet engine runs at temperatures exceeding 1,700 degrees Celsius. That is hotter than the melting point of the turbine blades themselves. This is solved by running cooling air through microscopic channels inside each blade, creating a thin film of cooler air on the surface. The blades operate above their own melting point, surrounded by air cool enough to keep them intact. This materials engineering is one of the primary reasons that commercial aviation engines can run reliably for tens of thousands of hours between overhauls. The blades are simultaneously burning and being preserved. Every time a commercial flight lifts off, this process runs simultaneously in 2 to 4 engines, each producing tens of thousands of pounds of thrust, running at temperatures that exceed the melting point of every material inside them. The next time you sit in a window seat during takeoff and feel that acceleration push you back, that force comes from Newton's third law, applied through 4 precisely engineered stages of thermodynamics and materials science, all of it happening at temperatures your kitchen oven cannot reach by a factor of 10. Moving air backward. Moving the plane forward. It is exactly that simple. It is exactly that complicated.